Hello BC Calculus students, this is Mr. Johnson and we are continuing in section 8.2 on series. This is the second video and we're on page 20. In the first video we covered the geometric series test, which we call the second convergence test, and in this video I'm going to outline the first convergence test as well as the third convergence test. So the first convergence test is the easiest to perform. In our text, we study the geometric series test first, and then we study this one. But what we do is we organize our 10 convergence tests by giving you the very first one as the test for divergence, or you might see it as the limit test for divergence, or it may also be called the nth term test, because what you're looking for is as n goes to infinity, you're trying to calculate the limit of the particular terms and if they go to zero or not. So in other words, if you have, and this theorem number 6 above kind of outlines this, if you have a series that converges, then the limit of the a sub n term is 0. In other words, the only way for an infinite sum to converge to a value is if in the end, as you calculate your terms, those terms go to 0. If those terms don't go to 0, then there's going to be a sum that's going to continue to increase. And so if your series converges, then the limit of the nth term is 0. However, the converse, so if you do the limit of a particular term and it's 0, that does not mean that the series converges or diverges. It's unknown. So this test is a really easy one. However, if you get a limit of 0, it tells you absolutely nothing. You have to go a different route. So the first thing you do is you take a look at the limit of the nth term. If it's not 0, that means that the limit is 1, or the limit is -4, or the limit is whatever, then the particular series is divergent, because whatever that value is, you're going to continue to add that forever in the infinite sum. If the limit is 0, you absolutely know nothing, and you have to try a different test. And that's why we have 10 total tests. So this particular test is very simple. Let's look at an example, number 7. Does the series converge or diverge? So what you do is you take a look at the limit as n goes to infinity of n squared over 5n squared plus 4, and we get a limit value of 1/5. Since it's not equal to 0, then this particular series is divergent. In other words, you would add 1/5 every single time as you go out to the nth term. And so you would continue to add more and more and more and more. Keep in mind, and this is one of the huge challenges in this section, if we were to look at the sequence n squared divided by 5n squared plus 4, not the sum, but the sequence, as n goes from 1 to infinity, we would say that this is convergent to 1/5, because that particular sequence, as we list out terms, becomes a convergent value of 1/5. In other words, let's say that you have, I'm not going to even calculate this right now, let's say we have a sub 1, a sub 2, a sub 3, a sub 4, and so on. Okay, as we continue, we're soon at some point going to get 1/5, 1/5, 1/5, and so on. Well, we can see based on that behavior, that's why we take this limit. We can see that the behavior of this sequence is that it turns into 1/5, which is convergent to 1/5. However, with the series, we would have a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, and so on, and then we would soon get 1/5 plus 1/5 plus 1/5 plus 1/5, and so on. And you can see that because we're adding these 1/5 over and over and over again forever, the sum will continue to increase, and it is divergent. So while one analysis of the limit in sequences appears to be convergent, the analysis with the limit in a series appears to be divergent, and that's where we have some difficulty as we study these two ideas between a sequence and a series. All right, let's take a look at two very important series that you do need to memorize. The first is the harmonic. The harmonic would be the sum as n goes from 1 to infinity of 1 over n. And you'll see different renditions of this. For instance, you might see 2 over n or 5 over n. Those are still just the harmonic, they're just scaled. The harmonic is 1 plus +1/3, +1/4, and so on. and we have an nth term, and we continue. And you have to memorize that this is divergent. I'm going to prove it here in just a moment. Okay, so that's divergent. Must memorize that. The alternating harmonic, believe it or not, is very similar. However, it alternates, and it is convergent. We're going to get -1 plus 1/2 minus 1/3 plus 1/4, and so on. And this is convergent. So you need to memorize these two. They're super important. They show up all over the place. We'll look at the proof for alternating harmonic later when we do that alternating series test. But for the harmonic, I'll go ahead and prove this to you right now. Keep in mind that if you take the limit as n goes to infinity of the harmonic, you end up getting 0. So again, if you have the limit as n goes to infinity of 1 over n, you get 0. And the tendency is to say, well, that converges. Well, no, it doesn't. It's divergent. I'm going to show you why right now it's divergent. So when you take the limit and you get 0, that means you know nothing. You have to somehow take a different test. Okay. All right. Here's a little proof. This is more of a pattern analysis of the harmonic, and it shows that it is divergent. There's a variety of proofs for this. With this one, we're going to look at partial sums. So we have the second partial sum. I am going to skip some of these, by the way. So we have 1 plus 1/2. We have the fourth partial sum, which is 1 plus 1/2 plus 1/3 plus 1/4. And then I'm going to go out to the eighth partial sum. Okay, so what we have now is just 3 different partial sums. I am skipping certain ones on purpose. You'll see why in a little bit. And we're going to look at some behavior. So I'm not going to really touch the second partial sum right now, but the fourth one, we could say that this particular partial sum is greater than 1 plus 1/2 plus 1/4 plus 1/4. And the reason, the only difference here is that instead of 1/3, I'm going to make it 1/4. And obviously 1/4 is smaller than 1/3, so therefore this inequality is true. And if you were to combine these, and I'm going to do this in a certain way just so you can see a pattern, I have 1/2, and I'm going to add 1/4 and 1/4, which means I have 2 halves. And I know that's 1, but just bear with me, I'm going to write it as 2 over 2. So I have 1 plus 2 halves. When we take a look at the eighth partial sum, I'm going to compare this to 1 plus 1/2 plus 1/4 plus 1/4, just in a similar way that we did the fourth partial sum. But then I'm going to add 1/8 and 1/8 and 1/8 and 1/8. So instead of adding the value of 1/5, 1/6, 1/7, and then 1/8, I'm just going to compare each of these 3 to 1/8. Now clearly 1/8 is smaller than 1/5, 1/6, 1/7, and so therefore the inequality holds true. And now if we think about what this is equivalent to, we have 1 plus, this would be 1/2 plus 1/2, and all of these 1/8 would equal a half as well. And so what I end up having is 3 halves. Now this pattern continues, and I'm not going to keep on listing out partial sums, but I am going to jump ahead to the 16th partial sum. And the 16th partial sum would be greater than, and if you kind of notice the pattern that we're dealing with, it would be 1 plus 4 halves. And the 32nd partial sum is greater than 1 plus 5 halves. And we could continue with this pattern. Now, the particular pattern that's forming, I'll write it over here on the left, is that in this particular partial sum, we have 2 to the first as a representative of the partial sum. This is the fourth partial sum, which is really 2 squared. This is the eighth partial sum, which is 2 cubed. This is the 16th, obviously that's 2 to the fourth, and 32nd, which is 2 to the fifth. And if you notice, what we have forming this particular pattern is that this power, this relationship, is how many halves I have to compare the partial sum to. So the 3, the 4, the 5, and so on. That behavior is going to help us analyze the nth partial sum. So let's jump ahead to the sum of just simply 2 to the power of n. Now again, we calculated 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. And if we calculate the nth partial sum, it is greater than 1 plus n over 2, or n halves. Now remember, if we analyze the limit as n goes to infinity of the partial sum, so let's say in this case 1 plus n halves, if n is going to infinity, clearly we get a limiting value of infinity. We have this ever expanding value of 1 plus n over 2. And because of that, because that is smaller, so we're doing this comparison, because again, all of this in blue, all of this in green, all of those are smaller than the actual partial sum. That means that we have now pushed by divergence. We've pushed, because that smaller one is divergent to infinity, we've pushed the harmonic series to diverge. So what we can say, in the end here, is that the harmonic series is truly, in fact, divergent. And again, there are a handful of proofs that can show this, but I like that one because it looks at patterns and it looks at the behavior of these partial sums, which is something that we just recently talked about. So it's nice practice for that as well. Either way, you just have to simply memorize that the harmonic is divergent, the alternating harmonic is convergent, because those will continue to come up. Let's move on to the next page. Okay, we're going to change gears slightly. I know that we've jumped around a little bit, and there is a lot of material in this particular section. And so this is going to seem really random, so just bear with me, okay? I'm going to teach you a concept that's called partial fractions, and it's a technique of integration. So with integration, you have use substitution, you have long division. I'm going to teach you integration by parts later on in the year. This is a technique called partial fractions, and it is a way of calculating antiderivatives in an integral where another method would not be utilized. So for example, use subs are not going to be helpful. Long division is not going to be helpful. And so we're going to look at partial fractions. This will be a technique that we use in series, but right now we're just going to look at antiderivatives just for a moment. I'm going to show you the skill, and then we'll get back into what it means for our study of series, okay? So let's take a look at this particular example, example 8. If you were to try use substitution, it would not work. Long division would not work, and so we need to use the idea of partial fractions. And here's the concept of partial fractions. You start off with a particular fraction that you are able to factor the denominator. So you must be able to factor the denominator. If you can't, then you're unable to use partial fractions. Now, partial fractions is basically the opposite of combining fractions. So in the past, let's say you have 1/2 and you would add it to, I don't know, like 3/7. And the way you would do that is to come up with a common denominator, and then you end up getting your answer. We're doing the exact opposite. We're going from the answer, and we're going to basically decompose the fraction. We're going to come up with two things that we were able to add together or subtract together in order to get the fraction. And we're just going to call the numerator of the first A, and we're going to call the numerator of the second B. It really does not matter the order as well as how you call that. You just have to label some value, and we're going to solve for A and B in order to decompose this fraction. So we're going to break apart the fraction. Your first step, and this is just an algebraic approach, so those of you that are good at algebra, you're going to be totally fine. We're going to multiply everything by the product of denominators so that we can clear all the fractions. So as we move over across the equals, we clear that and simply get 8, and we multiply our fraction here, a over x plus 2. The x plus 2's cancel, and you're left with simply a times the quantity x minus 2. And then the same with b, except this time the x minus 2's cancel, and you're left with x plus 2. All right, now we need to solve this equation, and you can let x be really anything you want it to be, and you're able to come up with a value of a and a value of b that make the equation true. We're going to use a technique that's just to pull out the number of x that makes the most sense and allows us to solve more quickly. So I'm going to let x be 2, because again, I can let x be anything I want. But if x is 2, then 2 minus 2 cancels a, and we're simply left with 8 equal to b times x plus 2. Remember, x is 2, so we have b times 4, and we have b equal to 2. So that's one item that we need. We're also going to let x be -2. Again, you could let x be anything you want, and you'll get some sort of system of equations that allows you to solve. I'm just picking values that make it easier to solve, make it more a much more fast process for us. So we plug in, we have b canceling this time because -2 plus 2 is 0. We have a times -4, and that gives us a equal to -2. Don't read into this, okay? These are not always the same but opposite signs. In this case, they happen to be the same value, just opposite signs, which is okay. All right, so here's what we've done. We have essentially set up the fraction 8 divided by x plus 2 times x minus 2, and we're rewriting this, simplifying it down into the fraction -2 divided by x plus 2, because a was -2, and I'm looking up here at the original. And then we have plus b is 2 divided by x minus 2. So I've decomposed this fraction. In other words, if you were to combine these two fractions by coming up with a common denominator, you would get this single fraction. Now, we were unable to integrate the one on the left because we just didn't have any technique for that. And so let's just go ahead and integrate the one on the right. Now, the integral can be separated because of addition. So we have the antiderivative, -2 natural log of x plus 2 plus 2 times the natural log of x minus 2. And of course, we have some constant value. So we've been able to successfully take the antiderivative now, which is exactly what we were shooting for. What I'm going to do is I'm going to factor out, because none of our answers match this, so I'm going to factor out a -2. I get natural log of the absolute value of x plus 2 minus the natural log of the absolute value of x minus 2. If you remember with properties of logarithms, in this type of situation, we have the natural log of x plus 2 divided by x minus 2, and then plus c. And if we go to our answers, we have option C. So this is not a short process, but as you practice, this is actually a very doable technique. You just need to know when to use it. Okay, let's go ahead and move on to the next one. I'm going to show you just a couple more of these. So if you feel like you have the hang of it already, that is excellent, and you can certainly pause or just fast forward the video. You can pause and check your work and try it yourself. It's up to you. Again, the denominator needs to be factored, and we have a divided by x plus 2 and b divided by x plus 1. By the way, if you do this with a friend, you may have different a and b values. The final answer should be the same. So if you try it on your own and you do something differently than I do, that's okay. As long as you do the algebra correctly, you should be just fine. Okay, we're going to multiply by x plus 2 times x plus 1. So we get 5x plus 8 equal to a times x plus 1 because the x plus 2 cancels, and b times x plus 2 because the x plus 1 cancels. We're going to go ahead and let x equal -1 so we can cancel a. On the left side, we have 5 times -1 plus 8. That's going to be 3. And we have a canceled and then b times +1. So we end up getting b equal to 3. Then we're going to let x be -2. So on the left, we have 5 times -2 plus 8, which is -2. And a times -2 plus 1, so that's a times -1. And that means that a is +2. All right. Our fraction now is 5x plus 8 divided by x plus 2 times x plus 1 equal to a is 2 divided by x plus 2, b is 3 divided by x plus 1. And remember, we were unable to integrate the beginning form of the problem, but now we can go ahead and integrate what we have left and our decomposition of these fractions. Now we're taking the integral from 0 to 1. Let's go ahead and find the antiderivative. So our antiderivative is 2 times the natural log of x plus 2 plus 3 times the natural log of x plus 1. And we're going to evaluate this from 0 to 1. So we have our upper value, which is going to be 2 times the natural log of 3, because I'm plugging in 1, plus 3 times the natural log of 2, because I'm plugging in 1, minus 2 times the natural log of 1 plus 2, sorry, 0 plus 2, so 2, plus 3 times the natural log of 1. All right, we need to simplify this down clearly to find our answer. So one of the properties of logarithms that we can use is we can take this value 2 that's multiplying the logarithm and raise the argument to that power. So this is really the natural log of 3 squared. This would be the natural log of 2 to the 3rd power. And if we do that, we get, let's see, we get natural log of 9 plus natural log of 8 minus the natural log of 4. And since the natural log of 1 is 0, that can cancel. And so now we're going to just combine. Remember, if you add logarithms like this that have the same base, you multiply the argument. And then we had this in the last problem. You divide. And so what we get is the natural log of 18, which is option C. All right, let's move on to the next page. All right, we're going to do one more of these. Again, if you feel confident with the skill, you can certainly fast forward or you can pause and try on your own. I'm just going to work through this one again, assuming that we might still need a little bit of practice on this concept that we just learned. So we have x minus 5 and x minus 2. And again, you have to be able to factor it. Oops, sorry. So we have a divided by x minus 5, and then b divided by x minus 2. And we're going to multiply this whole thing by the product x minus 5 times x minus 2. All right, so then what we get is 1 equal to a times x minus 2 plus b times x minus 5. And then we're going to go through the process of finding an x value that allows us to solve quickly. So we get 1 equal to b times 2 minus 5, so b times negative 3. And then that will give us, let's see, b equal to negative 1/3. That's a little different than we've been used to. And then we're going to let x equal 5. That gives us 1 equal to a times 3. So we get a equal to positive 1/3. All right, let's go ahead and set up our problem now. So we have 1 over x minus 5 times x minus 2. And we have now decomposed this. What I'm going to do, let's see, I want to make sure this makes the most sense. So I'm going to do 1/3 divided by x minus 5. I know that looks weird, but just bear with me. Plus negative 1/3 over x minus 2. Now again, what we're doing is we're going to integrate this. But before I do that, I'm going to factor out the 1/3 because it's going to make life easier for us, I think. So we get 1/3 times the integral of 1 over x minus 5 minus 1 over x minus 2. And I'll just keep that 1/3 in the front, which will help. So we have the natural log of the absolute value of x minus 5 minus natural log of the absolute value of x minus 2. And then, of course, we have the plus c. Keep in mind that the 1/3 is impacting the c, but it's still just a constant. So we can just worry about it as just plus c. Okay, remember combining logarithms, we have the absolute value of x minus 5 divided by x minus 2. And then we have plus c, and that's going to be our final answer, which is option E. Okay, so hopefully the idea of partial fractions or decomposing fractions makes some sense, because now we're going to go back into the idea of series. So we're going to get back into what we've been talking about. There is a little theorem here that we do need to use before we do that. We have utilized the idea of a constant in front before, but keep in mind that if you're multiplying by a value, you can pull that off to the front, and you can analyze the series and then multiply by that constant value. These are the two we're going to use here in the next set, and that is that if you have two different series that are convergent, then we're able to separate and analyze them separately and add the result or subtract the result. Okay, we're going to talk about the third convergence test. So your very first convergence test, and there's a beautiful summary on page 26 of your notes. But the first convergence test is the nth term test or the limit test or the divergence test, however you want to say it. You're taking the limit. If the limit is not 0, then the series diverges, you're done. If it is 0, you're not done. You have to move on and try something different. The second convergence test is the geometric series test. Remember, that's in the form of a r to the n minus 1, and we have the restrictions. You can look back on that test. Here's the third convergence test. It's called the collapsing sum or the telescoping sum. And this is a really cool test. That's a nerdy statement, but it's a cool test because what happens is that you decompose the fractions, you use partial fractions, and you're able to not only prove that it's convergent, but we can actually find the sum with this technique, which is pretty remarkable. I will tell you that this is not a very common technique. Geometric series show up all over the exam. This one does not show up all over the exam, but it does show up, so it's important to know this one. All right, we're going to show that this particular series is convergent, and then we're going to find the sum. So we're going to start off with a decomposition of fractions based on the technique we just learned. So we're going to multiply everything by n times n plus 1. So we get 1 equal to a times the quantity n plus 1 plus b times the quantity n. We will go ahead and let n equal negative 1. So we get 1 equals b times negative 1. So b is negative 1. And we're going to let n equal 0. And if that's the case, then a equals positive 1. All right, so what we have then is instead of the series from 1 to infinity of 1 over n times the quantity n plus 1, we now have written this as the series of, let's see, a, so 1 over n minus 1 over n plus 1. Now we're going to split this up and think about each of these terms of this series, but what I'm going to do as a technique is I'm going to start listing terms. And when I list terms, I think you're going to see a pattern that's going to start to form, and I think it's going to be helpful to see the collapsing style of this particular series. So first I'm going to use n is equal to 1, the very first term, and I'm not going to combine these. I'm just going to write them as a set. So that's going to be, if I was to plug in n is 1 and n is 1, I get 1 over 1, so I get 1 minus 1 over 2. If n is 2, I get 1 over 2 minus 1 over 3. If n is 3, I get 1 over 3 minus 1 over 4. If n is 4, I get 1 over 4 minus 1 over 5. And you can start to see that there's a pattern that forms. Okay, if this pattern continues, the nth term would be 1 over n minus 1 over n plus 1. So in other words, what we've done here is we've just set up the s sub n sum, the partial sum of the nth term, okay? And notice that there is some cancellation that's going to take place. So for example, I have negative 1/2 and plus 1/2. And I know I have parentheses here, but that's just to help show the n terms. N is 1, n is 2, n is 3, and so on. We have negative 1/3 plus 1/3. We have negative 1/4 plus 1/4. We have negative 1/5, and clearly something in here is going to cancel with that one. Clearly something in here is going to cancel with 1 over n. However, we are left with two little pieces to this. Specifically, we're left with 1, and we're left with negative 1 over n plus 1 that wouldn't happen to cancel with any other portion of this partial sum. So this partial sum, we could simplify down to just 1 minus 1 over n plus 1. Now remember, if we're able to take the limit of this as n goes to infinity and get a value, then we can state that that value is the convergent value of the series. In other words, I'm going to take the limit of s sub n, which is the limit as n goes to infinity of 1 minus 1 over n plus 1. and I get 1. Remember that in our notes was labeled as S, and it said that if we get a value like that, where we get this convergent value of the limit, then the series, our original series, from n is equal to 1 to infinity of 1 over n times the quantity n plus 1, must converge to the same value of 1. So we're showing that it's convergent to 1 using this third technique, which is the collapsing sum or the telescoping sum technique. Let's move on to the next page and try one last one on this topic. All right, so example 12, we're going to do one more of these collapsing sums, and we're going to combine it with another type of series that we've been studying. So first of all, and a lot of this we've done already in the past, so we have this particular series where we have 3 divided by n times quantity n plus 1. We've already done that portion of it. So I'm just going to using the properties of series that I showed you on page 22. We're going to split this up and we're going to factor out that 3. So we have a situation that looks like this, where we have these two different elements. Now, this first one right here, we already studied in example 11. We had the collapsing sum, which gave us a value of 1. So that's just 3 times 1, which is, of course, just 3. So that's going to converge to 3. And over here, we have a geometric series because we have an R value of 1/2. We have an A value of 1/2. And based on the R value, it's convergent. So we're going to find the sum of that, which is 1/2 divided by 1 minus 1/2. We actually, if this looks familiar, we did this really early on here. We get 1 divided by 1, so we get 1. All right, so we have two different series that are combined through addition. They both converge, which means we can use all these properties. And in the end, we have a situation where we have 3 as one series convergent to 3, and the other one is convergent to 1. And so together we get a series that converges to 4. All right, we're going to stop, and that will be the end of this video. The last video in this particular section will cover sort of an assortment of problems that go over the 3 different tests that we've been covering. Keep in mind that on page 26, there is a really great review that covers the 3 different tests that we've gone over, as well as the harmonic series and the alternating harmonic series. And that's a great resource as you continue to build all these concepts as we progress through the chapter. Thank you.